So, here is a clearer picture of what I was talking about, which is when you dope the semiconductor N type, you find that the Fermi level EF moves above and towards the conduction band. So, this is the imaginary intrinsic Fermi level position, which is no longer valid because we no longer have a pure semiconductor. So, this was the Fermi level location when the semiconductor was pure, and we now doped it N type, which means we have increased the electron concentration, which means we need to now decrease the Fermi level, has to pick a place where EC minus EF has to be smaller, because the electron concentration varies as e to the power minus this gap, that EC minus EF gap. So, the Fermi level will have to move closer to the conduction band edge. Similarly, for p type doping, we have increased the hole count, which means we need to reduce the gap between EV and EF, and therefore the what do you say, the Fermi level moves closer to the valence band edge. So, now these equations, if you remember well, these are all based on the Boltzmann's approximation. So, we started off with the Fermi function, which was f of e is equal to 1 by 1 plus e to the power e minus EF by kT, and we assumed that e minus EF is much larger than kT. Okay. So, if you keep doping the semiconductor more and more, and let us say the Fermi level is pushed closer and closer towards the Fermi level, we will end up with the situation where EF is so close to the conduction band edge that EC minus EF is no longer greater than kT. It is, say, of the order of kT. It is no longer much greater than your kT. In those cases, okay, we call the semiconductor to be degenerately doped, okay, and that is a technical term, and by definition the point at which we start calling the semiconductor degenerately doped is the point at which EC minus EF, okay, EC minus EF, this gap, the Fermi level has gone so close to the conduction band that this gap has become less than 3 times kT. Okay, so at T equal to 300 Kelvin, kT is equal to about 0.025 electron volt, which is about 25 milli electron volts. So, 3 times that is about 0.075 electron volt, and when EC minus EF is less than that value, we say that the semiconductor, which is N type doped, is now degenerately doped, and a lot of the calculations have to be done more carefully, and we cannot make many of the assumptions we have made so far. Similarly, if you are going to dope the semiconductor p type and you start pushing the Fermi level closer and closer to the valence band, we will reach a point where EF is within 3 kT of the valence band edge, and once again we say that the semiconductor is degenerately doped p type. And once again we can't make many of the assumptions we have made. So, as far as this course is concerned, we will not look at degenerately doped semiconductors. We will be very much within this 3 kT threshold, and the Fermi level location will be well below these borders. So, if this is the border for this is say 3 kT, let us call these two energy levels just to be very clear. As far as this course and the tests and the assignments are concerned, if this is my EV and we will say this is EV plus 3 kT and that is EC minus 3 kT, we will only consider cases where the Fermi level, despite any amount of doping, lies in these regions within this band. okay, so that we can still comfortably go ahead and use all these simple calculation techniques to calculate your electron and hole count. So, now what does doping actually do? So, why is it, what is the physical intuition behind the fact that doping significantly improves the electron and hole count, okay? And what do you mean by doping? Let us look at this in a with a different perspective. Okay, we already looked at it as a first glance. We know what it does, how the dopant atom bonds with the silicon lattice and contributes an electron and or contributes a hole. But let us look at it more closely. So, when you dope, let us take an example of an n-type semiconductor. Okay. So, we have a silicon lattice. Okay. So, silicon has been our role model, and therefore, I keep using the word silicon for semiconductor, but that does not mean that these concepts are not valid for other semiconductors, alright. So, let us say you had your silicon lattice, okay. It had these four what do you say bonds to the other silicon atoms, and we replaced this silicon with your n-type dopant, which is a donor dopant, which is a species that had 5 electrons. So, 4 of them participated in bonding and the 5th one was free to move about in the lattice, and therefore, it left the donor with a single positive charge, because there is one electron more that should have been with the donor for charge neutrality, but is no longer with the donor, and therefore, there is a single positive charge. So, if you think about this species here, okay, this one electron and one positive charge, okay, what is the binding energy? What does the energy that is held these two species together, okay. One can imagine this to be something like an hydrogen atom. It is not exactly a hydrogen atom, because there are other electrons present in the donor, but considering the fact that it is a single positive charge and a single electron that was initially bound to this donor and which has now moved away from the donor because of ionization, the energy needed to pull that electron away is the energy required to do so in an hydrogen atom. So, that gives you a, by comparing it to a hydrogen atom, it gives you a good estimate as to the ballpark number for that energy. Okay, so that is what we are trying to do. We are trying to estimate what is that energy needed for me to take the electron away from the donor and push it into the conduction band. And by calculating that energy, we can actually calculate the energy level created by the impurity. Okay, so what does that mean? So, in a pure crystalline silicon atom, silicon lattice, sorry, you have your valence band edge, you have your conduction band edge, and if your crystalline lattice is perfect, it is perfectly crystalline, no defects, no impurities, then you do not have any states in the band gap. But the moment you start creating defects, you start adding impurities, you will start seeing states appear inside the band gap. And as we move towards more and more disordered materials, say you ultimately take it towards amorphous silicon or a glass, you will find that there is a density of states inside the gap itself. Okay, so, the gap is no longer clean, but we will not go to such extremes at this point. All we have done now is we have added a donor, we have added a impurity into the silicon. Therefore, there are some traps that have appeared, there have been some states that have been created inside this gap, okay. And the purpose of this study is to locate those states, okay, at what energy are those states sitting, okay. And we are going to do that by identifying the energy required to take the electron out from this little entity, which is a positively charged core and a electron around it. Now, if you compare it to a hydrogen atom, the energy required would be this with some corrections. Okay, it would be 13.6 electron volts, but we need to correct for certain elements, which is the permittivity of the material is different. Okay, so we need to bring in a relative permittivity. It can no longer be epsilon naught, which is 8.85 e to the power minus 12. It cannot have that value. You need to have a relative permittivity correction. Okay, so we bring in an epsilon r square term, and you also need to account for the effective mass of the electron. You can no longer use the mass of the electron as is used in vacuum, because you have the electron propagating through the lattice and you have this interaction with the lattice, which results in an effective mass of me star. So by taking into account these two corrections, okay, so we multiply it by a factor of me star by m naught and divide by epsilon r, which is the relative permittivity of the semiconductor, epsilon r square, which is where epsilon r is the relative permittivity of the semiconductor, and continue using a 13.6 electron volt energy. Okay. So if you make these corrections, if you take into account these corrections and plug in numbers for silicon, so me star is with the same order as m naught. Okay, it is not orders of magnitude different. It could be slightly more or slightly less depending on the different semiconductors. And for silicon, epsilon r is of the order of 11.7, say let's call it 10, okay, just to give you an easy calculation. So the binding energy is about 13.6 electron volt into something which is the order of 1, which is your me by m naught, divided by 100, okay, which is about 0.1, give or take 0.1 electron volt. In fact, it is less than 0.1 electron volts. Therefore, this trap energy is actually located, the moment you add a donor, what this is saying is that the moment you add a donor, you are creating a trap state, or you are creating energy states due to this donor, which is located at energy level ED. Okay, so this is something called as the donor energy level or the donor level, and this ED is located at around 0.1 electron volt from the conduction band edge. So in the case of silicon, your band gap, this is about 1.12 electron volts, and this donor dopant has led to the creation of states inside the band gap, and those states are located at around 0.1 or in fact less than 0.1 electron volt. That is about 10% of the band gap, 0.1 electron volt from the conduction band edge. So what does this mean? It means that this donor, which was initially charged neutral, had a positively charged core and had all its 5 electrons. Okay, so this was the charged neutral species. Okay, and this was charged neutral, let us say temperature T equal to 0. But the moment the temperature increased a little, these electrons gained enough energy, they gained this 0.1 electron volt energy to snap away from the donor and to get into the conduction band of the lattice. Therefore, these donors that lost their 5th electron all became positively charged. So in other words, they were ionized, and these electrons which left the donor and moved into the conduction band were now free to conduct. Okay, so we have increased the electron count in the lattice, the free electron count in the lattice. So when I say electron count, just as a means of speaking, I mean it's just the it is understood that it is the free electron count. Okay, so we are really not interested in the electrons in the valence band. There are plenty of those. So the addition of the donor has increased the electron count, the free electron count in the conduction band, and it has now become positively charged because of it getting ionized. And since the donor level is located so close to the conduction band edge, it really does not take too much of temperature to activate these electrons, okay, to ionize these donors. So at 300 Kelvin, in the case of silicon, we are able to promote the electrons sitting in the valence band. If you were to consider your pure intrinsic semiconductors, pure intrinsic silicon, at 300 Kelvin we can promote about 1e10 per cc electrons from the valence band to the conduction band, and that is at an energy gap of 1.12 electron volt. Here I have a gap which is 10% of the original energy gap, which is 0.1 electron volts because of these donors, and therefore it is much easier to ionize these donors. This can happen at a much lower temperature. We can ionize these donors and promote all these electrons into the conduction band, and therefore the addition of a donor like dopant can significantly improve the electron population. Okay. The same argument can be made for holes. So that's what the doping, that's what doping is doing if you look at it from the perspective of the energy levels and the creation of these traps inside the gap. So now let us calculate again. Okay, so we know we want to calculate the free electron concentration and the hole concentration in the valence band after doping, right. So this calculation is straightforward, it is just Nc e to the power minus Ec minus Ef by kT. So that is the calculation, okay. But then there is a much nicer or a much more intuitive or much more useful relation that you can get. Now since, so let's draw this, that is Ec, that is Ev, and now you have some Ef which is different from your Ei. Ei is just offset from mid gap, it is close to mid gap, so I will just locate it there. So that was the Fermi level for a pure semiconductor, but now after doping the Fermi level is shifted to Ef, and if it is n type doping, it is Ef is going to be closer to Ec. Now this expression tells you that the electron count is Nc, which is the effective density of conduction band states, okay, effective density of states in the conduction band, into e to the power minus Ec minus Ef by kT. But Ec minus Ef is also equal to Ec minus Ei, okay, so that is Ec minus Ei minus Ef minus Ei. So this term is essentially that minus this, and we can sort of split that expression by bringing in the Ei term here, okay. So why are we splitting this? Because this coefficient here is nothing but the electron concentration in the intrinsic semiconductor, because your Ef has now become Ei, okay. And for a doped semiconductor, this expression, this electron count is essentially this term into the exponent having an energy gap which is the difference between the new location of the Fermi level and the intrinsic Fermi level position. So this expression is essentially Ni e to the power Ef minus Ei by kT. So these two expressions are identical. So you could count your electrons by saying it is Nc e to the power minus Ec minus Ef by kT, or we could say that it is Ni e to the power Ef minus Ei by kT. So this expression relates, both of these expressions are useful, okay. It depends on the situation. This expression relates the carrier count by noting down the energy difference between the conduction band edge and the Fermi level, whereas this expression makes the carrier count by noting down the energy difference between the new Fermi level position and the intrinsic Fermi level position. Okay, so this is the Fermi level position for a intrinsic or a pure semiconductor, and after doping it is relocated to EF, and this expression can tell you what this new Fermi level, how far this new Fermi level moved away from EI. Okay, so both these expressions are useful, and we could create a similar expression for the holes, which is the whole population in the valence band is basically NV into e to the power EV minus EF by KT. We again bring in the EI, and you find that the whole population can also be represented as Ni e to the power minus EF minus EI by KT. So this expression, okay, so which is this expression here for the electron count and this expression here for the hole count, looks more or less similar, except for the fact that the exponential here has got a positive sign and the exponential here has got a negative sign. Okay, so that's the major difference. So now, what is N into P? In the case of an intrinsic semiconductor, okay, which can be what was the electron and hole count? In an intrinsic semiconductor, my EF was equal to EI, therefore this exponent is 1, and therefore the electron and hole count were both equal to Ni. Okay. So in an intrinsic semiconductor, we had N is equal to P is equal to Ni, okay, and the product Np was equal to Ni square. But what about the doped semiconductor? What is this product? Np, okay, is now equal to Ni e to the power Ef minus Ei by Kt into Ni e to the power minus Ef minus Ei by Kt. These two terms cancel, and therefore this product is still equal to Ni square. So irrespective of whether the semiconductor is doped or intrinsic, the electron count into the hole count is always equal to Ni square, provided the semiconductor is at thermal equilibrium, which means that you have taken the semiconductor, you have either kept it intrinsic or doped it, you have taken the semiconductor and you have kept it in the dark, you have not applied any light, you have not applied any voltage, you kept it in the dark as it is, with the only influence on the semiconductor being due to temperature. So that is thermal equilibrium. So every process that is going on inside the semiconductor is very nicely balanced by a reverse process. So there is nothing changing. I mean there are many things going on. You are creating a lot of free electrons, you are losing a lot of free electrons, all this is going on, but it is all balanced in a very nice way that statistically speaking the intrinsic carrier concentration is fixed, and the other properties of the semiconductor is not really varying with time. Okay, so that's what you mean by thermal equilibrium. And this property that Np is equal to Ni square is very useful, because if I know my electron count and I want to find my hole count, I just need to do Ni square by N. Okay, so this gives me my whole population. So this relation that the Np is equal to Ni square is something called as the mass action law. Okay, and this might appear to be a very odd looking term. What is the meaning behind mass action law? Well, it essentially comes from looking at chemical reaction rates. Okay, so you can think of it as a chemical reaction that is going on. Okay, and what is the reaction? It has got to do with the generation and the recombination or the loss of these free carriers. Okay, and we will talk about that later. So that's the process that's going on, and just like how you sort of consider reactants in a reaction, for a chemical reaction we consider the electron and hole count in this process of thermal generation of carriers and thermal recombination of carriers, which we will talk about soon. So, what does doping do? So, we looked at, we now have a good understanding of what doping does in terms of equations, but it is always nice to look at this graphical picture. Okay. So, let us go back to our picture of intrinsic semiconductors. Okay. So, this was my density of states. There are many plots drawn on this, so please do not get confused. So, that is the density of states. So, that is density of states versus energy. This dotted line is the Fermi function, it is f of E versus energy, and as we noticed it takes a value of half when it crosses E is equal to EF. And since this is an intrinsic semiconductor, this EF is equal to EI. Okay, so that is my intrinsic semiconductor position. And we already saw that the electron count was basically the product of the density of states in the conduction band and the probability of finding carriers in the in these states. So, that was my electron count, which is this product, and that is the hole count. Now, by doping, what we have done is, if we dope it n type. Okay, so, this is the intrinsic case, your n is equal to p is equal to ni, np is equal to ni square. If you dope it n type, we have added a donor dopant, and let us say this is my imaginary EI, this was EI in the intrinsic semiconductor. By adding a donor dopant, we have increased the electron population and we have effectively moved EF closer to the conduction band edge, and it is located above EI. Now, since the Fermi level is located at a different location from EI, the Fermi function shifts. Okay, it is no longer going to remain the same. It is now going to adjust itself so as to take a value of half in this point. Earlier the Fermi function was taking a value of half at EI, but now it is going to take a value of half at EF. Okay, because earlier EF was equal to EI. So, and now EF is not equal to EI. So, if the Fermi if you can imagine the Fermi function as having moved up a little, okay, along with EF, okay, then it is very clear to see that the probabilities here have now suddenly increased. The values which were initially very small. So, let us say initially the value here was less than half, let us say it was 0.2. But now since we have moved the entire f of E curve upward, this value is now much greater than 0.2. Okay, okay, at here it was half, which is 0.5. So, here it could now become 0.3. That is the value of f of E, which means the probability of me finding an electron in these states has increased. The density of states has not changed. Okay, it is not going to change unless you dope it very strongly. We are not talking about those levels of doping. The density of states has not changed, but the probability of finding an electron in those states has increased in the case of n type doping. The probability of finding electrons in the states above EF have increased in the case of n type doping. And it is not only that the electron population is increased. So, now the electron population is increased significantly. Okay, so, you can see that this shaded region has got a larger area as compared to this region here, which was the intrinsic case. Okay. It is not only that the electron population is increased, the whole population has also decreased. Okay. Why is that? Because this is the Fermi function. Let us say this is the value of 1, it is asymptotically heading towards 1 as we go to minus infinite. and the probability of finding a hole depends upon this difference, it is 1 minus f of e. Okay. Now initially the probability of me finding a hole at say some energy level here was 1 minus f of e, let us call that as say 0.2. But since we have shifted the entire Fermi f of e curve upward because EF has gone up, these values are now suddenly decreased. So what was 0.2 at some energy level there has now become a much smaller number, let us say it is 0.1. These are just numbers, I am just these are not calculated values, these are just numbers I am putting out in order to get the message across. So what was the 1 minus f of e was much larger in the intrinsic case, but the moment we doped it n type, 1 minus f of e for energy levels E less than EF have suddenly gone down, okay, which means the probability of me finding a hole in these states has suddenly gone down. And therefore, while the electron count has increased, the hole concentration has decreased. The area under this curve, which is symbolizing the whole population, is now become less than the case of the intrinsic semiconductor. So in an intrinsic semiconductor, the number of holes were Ni, the hole concentration was Ni, the electron concentration was Ni. In an n type semiconductor, the electron concentration is greater than Ni, but the hole concentration has gone less than Ni. And how much less? If n is the electron concentration, the hole concentration has to be Ni square by n. In the p type semiconductor, the opposite happens. If you have doped the semiconductor p type, we have moved the Fermi level down. So this is my intrinsic Fermi level position, that is EI. We have now moved the Fermi level below EI, okay, and f of e has to shift downward in order to take a value of half. So you can think of f of e as sort of pinned to this Fermi level position, right. So if this is EF, imagine a sort of a pin right there, because it always has to take a value of half. So as we move this up and down, this entire curve also has to move up and down, it has to move either up or it has to come down. Okay, so that is f of e responding to the relocation of EF. So by now moving EF downward, f of e is also shifted downward, which means that the probability of me finding an electron has now gone down drastically. So it was 0.2 there, it had increased to 0.3 for n type doping, but now it has become 0.1, let us say 0.1. The probability of me finding an electron in the states above EF has gone down. So although the density of states has not changed, the number of electrons in the conduction band has decreased, and it will decrease to a value less than Ni, which was the intrinsic case for p type doping. For n type doping, the electron count is increased, electron concentration is increased. And similarly, if you look at 1 minus f of e, that is this gap, since the Fermi level has now moved down, and it has brought f of e along with it, this value of 1 minus f of e has now increased, which means that the probability of finding a hole in the states below EF has now gone up, and therefore my whole population has now suddenly shot up. The whole count in the valence band states has now gone up. Okay. So here in case of p type doping, my electron count is going to be less than Ni and the whole count is going to be greater than Ni, and in all cases n into p is equal to Ni square. So if I know my electron count, I can find my whole count as Ni square by n, or if I know my whole count, I can find my electron count as Ni square by